bond parameters. So covalent bonds, they are characterized by certain parameters such as bond length, bond angle and bond energy. First, bond length. So what is bond length? It is the distance between the center of the nucleus of two bonded atoms in a molecule. For example, A and B are two atoms. They join to form a molecule. So this is the center of A, this is the center of B, and the distance between the center of the nucleus of these two bonded atoms is known as the bond length. So this R is the sum of the covalent radius. So how we define covalent radius? See, we have already studied that covalent radius is 1/2 of the distance between the nucleus of two covalently bonded atoms of the same element in a molecule. For example, this is hydrogen, one atom of hydrogen, another atom of hydrogen. The two join to form hydrogen molecule. This is the internuclear distance, that is 74 picometer, and 1/2 of this distance is your covalent radius, right? So this is regarding the covalent radius. So we have already studied here that this covalent radius, this is measured as the radius of an atom's core which is in contact with the core of the adjacent atom in a bonded situation. So this, I hope it is clear that this covalent radius is the radius of the atom's core. This is the core of the atom, and this core is in contact with the core of the adjacent atom in a bonded situation. Now we have discussed about the van der Waals radius, which we know is greater than the covalent radius. So this van der Waals radius, it represents the overall size of the atom, and this includes its valence shell in a non-bonded situation. Now let us see the van der Waals radius. It is 1/2 of the distance between two similar adjacent atoms belonging to two nearest neighboring molecules of the same substance in the solid state. For example, this is a chlorine molecule, this is a chlorine molecule, and these atoms are not bonded. So I take the internuclear distance between them, and that comes out to be 360 picometers. And 1/2 of this distance gives me the van der Waals radius. So van der Waals radius represents the overall size of the atom, which includes its valence shell in a non-bonded situation, right? Then we come to the factors which affect the bond length. The first factor is the bond multiplicity. See, the bond length decrease when the bond multiplicity increase. For example, the triple bond is shorter in length than the double bond, which in turn is shorter than the single bond. Then we see here nitrogen triple bond N triple bond N smaller than N double bond N, which in turn is smaller than N single bond N. That is, single bond is larger than the triple bond. So the other factor on which bond length depends is the size of the atom. So as the size of the atom increases, the bond length also increases. As we move down the group, say I take group 14, germanium is having more size. So the bond length is more in case of germanium, because as we move down the group, a new shell is added, so the distance of the valence electron from the nucleus increases. Bond angle. How we define the bond angle? It is the angle between the orbitals which contain the bonding electron pair around the central atom in a molecule. See, we will be studying in the further topics about lone pair and the bond pairs. So the angle between the orbitals which contain the bonding pairs around the central atom is called the bond angle. The bond angle is expressed in degrees, and this can be determined by spectroscopic methods, and the bond angle helps in determining the shape. Then we come to bond enthalpy. We know that when a bond is formed, energy is released, and the same amount of energy has to be supplied in order to break that bond. So bond enthalpy is defined as the amount of energy required to break 1 mole of the bond of a particular type between two atoms in a gaseous state. The unit of bond enthalpy is kilojoule per mole. For example, in case of hydrogen, The bond enthalpy is 435.8 kilojoule per mole. Hydrogen is having a single bond. And then we come to oxygen, which is having a double bond. We find that in order to break this bond, we require energy 498 kilojoule per mole. Then to break this nitrogen, which is having a triple bond, the energy required is 946 kilojoule per mole. So that means larger the bond enthalpy, stronger will be the bond in the molecule. We know that triple bond is stronger than the single bond. Then we can also say that the bond dissociation enthalpy or the bond enthalpy depends upon the size of the bonded atom. If the size of the bonded atom is small, the bond formed is stronger, and so the bond enthalpy will be large. For example, in case of hydrogen, the bond enthalpy is 435.8 kilojoule per mole, and chlorine, which is having a larger size than hydrogen, is having a bond enthalpy of 243.5 kilojoule per mole. So bond enthalpy depends upon the size of the bonded atom. Smaller the size, greater is the value of the bond enthalpy. That means stronger is the bond. Then the second thing on which the bond enthalpy depends is the bond length. Shorter the bond length, larger will be the value of the bond enthalpy. For example, we know that in case of triple bond, the bond length is less. So when the bond length is less, the value of the bond enthalpy is going to be more. Now we come to the concept of average bond enthalpy, and this concept we take for polyatomic molecules. Now for example, what are polyatomic molecules? These are the molecules which contain more than one bond of the same type. For example, I take the example of water. So it is having two OH bonds. Now we find that in case of water, when the first bond is broken, the energy required is 502 kilojoule per mole, and in case of second bond, the energy required is 427 kilojoule per mole. So the difference in these delta H of atomization suggests that the second OH bond undergoes some change because of the changed chemical environment. That is, it is in a different chemical environment. As a result of this, its bond enthalpy is different. Now in this case, what we will do, we will take the average value. So this average bond enthalpy will be taken, and this will be 464.5 kilojoule per mole. Thus for polyatomic molecules, we will take the average bond enthalpy, right? Then we come to the next is the bond order. Now what is bond order? Bond order is the number of bonds between two atoms in a molecule. For example, in case of hydrogen, the bond order is 1. In case of oxygen, the bond order is 2. In case of nitrogen, the bond order is 3. In case of carbon monoxide, the bond order is again 3. So, more the bond order means the bond enthalpy is more, because when the number of bonds are more, then what happens? The bond enthalpy is more and the bond length is less, right? So with increase in the bond order, the bond enthalpy increases and the bond length decreases. Now we talk about isoelectronic molecules and ions. So isoelectronic molecules and ions, they have identical bond orders, right? For example, fluorine and O2 negative, they have bond order 1. They are isoelectronic because both are having 18 electrons. And in case of nitrogen, carbon monoxide and NO positive, the number of electrons are 14 in both the cases and the bond order is 3, right? So bond order tells us about the number of bonds which are present between two atoms in a molecule. We'll discuss more about bond order in the next unit. Resonance structures. The phenomenon of resonance was put forward by Heisenberg to explain the properties of certain molecules. It is observed that a single Lewis structure is not adequate for the representation of a molecule in agreement with its experimentally determined parameter. To understand, let's take the example of ozone molecule. Each oxygen atom has an octet of electrons. According to this structure, there is one single oxygen-oxygen bond and one oxygen-oxygen double bond. The normal oxygen-oxygen bond length is 148 picometer and the oxygen double bond oxygen is 121 picometer respectively. According to this structure, we expect that the two bond lengths in ozone molecule is unequal, but experimentally it is observed that both the bond lengths are equal, that is 128 picometer, and the bonds are intermediate between single and double bond. That is 128 is intermediate between 121 and 148 picometer. So this means that this Lewis structure does not account for the observed experimental fact. To solve this problem, an alternative structure was drawn. In this, the position of single and double bond was interchanged, but none of these two structures explain the observed fact. It is proposed that the actual structure is in between these two structures. In such a case, we say that the actual structure is a resonance hybrid of these two structures. The individual structures are called resonance structures or contributing structures. Let us now see the definition of resonance. So, when a molecule cannot be represented by a single structure, but its characteristic properties can be described by two or more than two structures, then the actual structure is said to be a resonance hybrid of these two structures. Let us now learn the conditions for writing the resonance structures. You can note down these conditions. The first is the contributing structures should have the same atomic position. The atomic position of all the atoms should be same. The contributing structures should have the same number of unpaired electrons. All the contributing structures should have the same number of unpaired electrons. Then they should have, the contributing structures should have nearly the same energy, and the structures should be so written that the negative charge is present on the electronegative atom and the positive charge is present on the electropositive atom. In contributing structures, the like charges should not reside on adjacent atoms, and we should, while writing the resonance structure, all this point has to be kept in mind. Right? Now we discuss about an important concept, that is resonance energy. We define resonance energy as the difference between the actual bond energy of the molecule and that of the most stable of the resonating structure. So let us see this energy profile. So this is the energy of the most stable of resonating structure, and this value, that is E naught, is the experimentally determined value, or we can say the actual bond energy. The difference between these two is known as the resonance energy, right? So characteristics of resonance: these contributing structures do not have any real existence. They are only imaginary structures, and they are proposed to explain the properties of the molecule. Only the resonance hybrid has the real existence. Because of resonance, the bond length in resonating structures become equal. For example, the oxygen-oxygen bond length in ozone is equal. All the carbon-carbon bonds in benzene are equal. The resonance hybrid has lower energy and has greater stability than that of the contributing structure. Greater is the resonance and resonance energy, greater is the stability of the molecule. And the concept of resonance is a theoretical concept. We can see these different resonating structures. This is the resonating structure for, these are the Lewis structures basically. You can see that the contributing structures are made by just shift in the double bonds. This is sulfur trioxide resonating structure. You know now how to write the Lewis structures. So this is for benzene molecule. Okay, in this only there is a shift in the, the double bond positions are interchanged, right? So this is the carbonate, and this is for nitridine, and this is for nitridine. So you can practice these structures. You know how to write the Lewis structure. I have already taught you. So please practice these. These are important and can come in the paper. Polarity of bonds. The existence of 100% ionic bond or covalent bond is an ideal situation. In reality, no bond is completely covalent or ionic. Even if we have a covalent bond formed between hydrogen atom, it will have some ionic character. When the covalent bond is formed between similar atoms, the shared pair of electron is attracted equally by the two atoms, as a result of which the electron pair is situated exactly between the two identical nucleus. Such a bond is known as a non-polar covalent bond. For example, if we take the example of chlorine, the shared pair of electron is attracted equally by the two atoms, and so such a bond is a non-polar covalent bond. Now we take the example of HF. In HF, fluorine is more electronegative, so it pulls the electron density towards itself. As a result of this, there is a creation of partial positive and partial negative charges. So we can say that the molecule has become polar. So such a covalent bond is an example of polar covalent bond. So covalent bond can be a polar covalent bond or a non-polar covalent bond. This is an example of a non-polar covalent bond, and this is an example of a polar covalent bond. Because of such polarization, the molecule is having a dipole moment, and this dipole moment is designated as mu and is mathematically expressed as charge into distance of separation between the charges. Its unit is debye, right? Now this dipole moment can be represented by a crossed arrow, which is put on the Lewis structure of the molecule. The cross is on the positive end and the arrowhead is on the negative end, right? So this dipole moment is also a vector quantity. Let us now see the case of polyatomic molecules. For example, I take the example of water. So in water, the dipole moment of the molecule is the vector sum of the dipole moment of the various bonds. So there are two OH bonds, and the dipole moment of these two gives a resultant, which is this. So this resultant dipole moment which is the sum of these two, has a value of 1.85 debye, right? Then we see the dipole moment of beryllium fluoride. This is 0. So why it is 0? Because the dipoles, they cancel out each other, right? They cancel the effect of, they cancel the effect of each other. So the dipole moment for beryllium fluoride is 0. Now we see the example of BF3 molecule. In BF3 molecule, the bonds, they are oriented at an angle of 120 degree, and the three bond moments give the net sum of 0 as the resultant of any two is equal and opposite to the third. So we see here that the resultant of this is represented like this, and the two, they cancel out each other. So the resultant dipole moment is 0 in case of BF3 molecule. Now we discuss about ammonia and NF3 molecule. They are represented like this. They both are having a pyramidal shape with a lone pair of electrons on the nitrogen atom. Now let us see about the dipole moment. In case of ammonia, the orbital dipole, this is the orbital dipole, which is because of the lone pair, and the resultant dipole of the NH bonds, they both are in the same direction. But in NF3, the orbital dipole, which is because of the lone pair, is in a direction opposite to the resultant dipole. So as a result of this, they cancel out the effect of each other. So the resultant dipole moment in NF3 is less as compared to the resultant dipole in NH3, where there is an additive effect, that the resultant of all these NH bond is pointing in the same direction as the orbital dipole, which is because of the lone pair of electrons, right? Now the information which is conveyed by the knowledge of dipole moment is, one, we can make a distinction between polar and non-polar molecules. Okay, the non-polar molecules, they have 0 dipole moment, whereas the polar molecules have some value of the dipole moment. then we can come to know about the degree of polarity in the molecule. For example, the greater the dipole moment, greater is the polarity in such a molecule. For example, HF is more polar than HCl. You can see the dipole moment. Then we come to know about the shapes of the molecule. Now, for example, water and carbon dioxide. We see water and carbon dioxide. They both are triatomic molecules. That is, they are made up of 3 atoms. But the dipole moment of carbon dioxide is 0 and that of water is 1.85 dpi. The reason is that this is a linear molecule and this is an angular molecule. So the net dipole moment of the OH bond is in this direction and it is having a value 1.85 dpi, whereas in case of carbon dioxide, the 2 dipole moments, they cancel out each other, and so the resultant dipole moment is 0. So from the knowledge of dipole moment, we come to know about that molecule is polar or non-polar. We come to know about what is the degree of polarity in the molecule. Then we come to know about the shapes of the molecule, right? So carbon dioxide is having a linear shape, and whereas water is having a angular shape. Then also one more information we come to know from the knowledge of dipole moment is the ionic character in a molecule. Now, if the difference in electronegativity of the 2 atoms is large, the bond will be highly polar. We can sum up all this like when the electronegativity difference between the atom is 1.7, then the bond is 50% ionic and 50% covalent. And if the electronegativity difference is more than 1.7, then the chemical bond is predominantly ionic. And if it is less than 1.7, the bond is mainly covalent. So larger the electronegativity difference, larger will be the ionic character. Let's now discuss the partial covalent character in ionic bonds. See, dear students, we have already discussed that the covalent bonds have ionic character. This was explained by the dipole moment. Now, similarly, the ionic bonds also have what? The covalent character. This is explained by the Fajan rule. Before going to the rule, let us understand an important definition, that is polarization. Now, what is polarization? For example, we have oppositely charged ions A and B. When they are brought together, the positive ion attracts the outermost electrons of the negative ion. As a result of this, there is a distortion of the electron cloud around the anion towards the cation. This distortion of electron cloud of the negative ion by the positive ion is called polarization. If polarization is small, the bond is mainly ionic. But if the polarization is large, then the bond acquires the covalent character. For example, let us see, this is a case when the 2 ions, they are shown without any polarization. Then this is when there is polarization, the cation polarizes the anion. See, cation has polarizing power and anion has polarizability. Okay, so this has the power to distort the electron cloud, and this should have the polarizability to get distorted, right? So what polarization means? It is basically what? The distortion of the electron cloud, right? So what happens? The positive ion, it polarizes the negative ion and draws the electron towards itself. As a result of this polarization, there is a decrease in the positive charge on the cation. This decrease is because of the neutralization of the charge. See, when the charge cation attracts the electron cloud towards itself, then what happens? The negative become less and the positive also become less. See, why this positive charge becomes less? Because it is neutralized by the electron cloud of the anion. So as a result of polarization, there is a decrease in the positive charge, and this decreases because of the neutralization of the positive charge by the electrons, right? So as a result, there is a decrease in the positive charge on the cation and decrease of negative charge on the anion. Whenever there is a decrease of positive and negative charges, then definitely this is leading to what? The covalent character. Now, when polarization is more, there will be more of the covalent character. This tendency of the cation to polarize and the polarizability of the anion, they are summarized in the form of rules which are known as Fajan rules. The first is small size of the cation. Small the size of the cation, greater will its polarizing power. For example, if I take the example of lithium and sodium, lithium chloride, lithium has smaller size as compared to sodium, so it has greater polarizing power. As a result of this, lithium chloride is more covalent than sodium chloride and potassium chloride. Then the other thing is large size of the anion. So polarization increase when the size of the anion increases. For example, if I see the covalent character of lithium halides, I find that lithium iodide is having greater covalent character as compared to lithium bromide, which is greater than lithium chloride and in turn greater than lithium fluoride. So in this, iodide is having a larger size, so it has greater polarizability, right? So the electron cloud on the bigger anion will be held less firmly by the nucleus, and therefore it would be more easily deformed towards the cation. So larger the anion, higher will be its polarizability and more will be its covalent character. Then large charge on the ion. If the charge is more, then definitely the polarizing power will be more. So larger the charge on the cation, greater will be its polarizing power, and large charge on the anion, greater is the tendency to get polarized. For example, if I take sodium ion and calcium ion, so the charge is more on calcium ion. As a result of this, calcium chloride has a higher covalent character than sodium chloride because of greater charge on calcium ions, right? Then we come to the electronic configuration of the cations. Cations which have 18 electron shell configuration, they have greater polarization than the cations with 8 electron shell configuration. This is because when we say that there is an 18 electron shell ion, it is going to have 10 d electrons, and we know that d electrons have imperfect shielding, so they have increased effective nuclear charge. As a result of this, the ions, they behave as though they are under the influence of a greater nuclear charge and thus polarize the anion to a greater extent. For example, if I talk of sodium chloride and CuCl, CuCl is slightly covalent and so it is insoluble in water, whereas sodium chloride is ionic and is highly soluble in water. Thus, according to Fajan rule, the covalent character is favored by small size of the cation, because smaller the size of the cation, greater is its polarizing power. Large size of the anion, large is the size of the anion, greater is its polarizability. Then high charge on cation and anion. If there is a high charge on cation and anion, greater will be the polarizing power. And if the cations have 18 electron shell, that means it have d electrons, and we know that d electrons have imperfect shielding. As a result of this, nuclear charge will be more, and when the charge will be more, then definitely the polarizing power is going to be more.